You
So
mean just run it like this?
present without playing and we can see everything.
Well, that's interesting. Okay. Well, high tech and interstellar communications. So, okay. Well, this is our team. As long as you can see some of the data, that's okay. And we call ourselves Whale SETI, and sometimes F sub I. That refers to the Drake equation term of the fraction of species that express intelligence. So I wasn't sure exactly this group. I'm kind of the odd man out because I do SETI and extrasolar planets, but also information theory. And I learned what a conspecific was when I was already deeply into animal communication stuff. Everybody kept using this word. So I'm coming up to speed still after all these years. So I thought I'd run through SETI just for a few minutes. The main talk is not about SETI. It's about applying information theory and interesting things you can do with it. If you're doing regular SETI, you can extend the radio to putting radio telescopes like Arecibo was on the far side of the moon. But what if you get a signal that sounds like this?
Sadly, we're not getting your audio.
I can do it. Oh. Here you go. Hold on, Laurance.
Let's see. Yeah, good. We're getting it locally.
Did everybody hear that okay?
Yes.
Okay. So what if that's coming from space? What do we do? Well, radio astronomers I've played that for are at a loss. So what we need are intelligence filters, some way to tell if that's an intelligent signal. And so SETI really relies right now on narrowband transmissions. I'll run through other ways of doing SETI and we'll come back to radio in a second here. One way of doing SETI is to use the planets that Kepler found, especially ones that transit in our line of sight, because that means the Earth transits in their line of sight. And so that's a preferred SETI target. Another way to do SETI is to look for the natural carbon dioxide microwave laser that is produced in the Martian atmosphere. So if you have a solar system that consists of an Earth-like planet in the habitable zone and they have a Mars, it would, in a couple hundred years at most, we're going to utilize Mars's natural microwave laser to, surround Mars with mirrors and transmit interstellar distances doing optical SETI. Optical SETI is reliant upon pulses, very fast pulses that we know nature can't make, like a millisecond pulsar is about as good as nature can do, but with computers and technology, we can do nanosecond connections like Bluetooth. Another SETI is relying upon orbital angular momentum in a single photon. Turns out you can twist a single photon up to 40 times and actually transmit data of up to 40 bits. That's a trillion pieces of information. So detecting single photons, if you're a very advanced civilization and you know about orbital angular momentum, then you can look for twisted photons. This is just real sketchy. Happy to answer questions on any of this. And of course, we have the other technological detection. And there's a linear accelerator just south of us here, or west of you guys, at Stanford, and it puts out a neutrino lighthouse beam. So in other words, there are ways of doing SETI that will detect extraterrestrial technology. And finally, there's, of course, quantum teleportation, which is the least utilized so far. But if you're a very advanced civilization, you want to distribute entangled particles throughout the universe and then use teleportation to transmit information. But really, what we need right now with radio SETI is, an optical SETI for that matter, is an intelligence filter. SETI up till now has relied upon very narrow band transmissions because nature, you tune onto a radio channel and you turn the dial once, you're on a new channel. Well, that's technology. And if you turn more than 1 hertz, well, the narrowest band signal from nature is called an OH maser, and it's about 300 hertz wide. So in other words, in this upper right hand, there are 2 facilities doing SETI right now, the Allen Telescope Array, which is kind of a net. If you don't know where the fish are, you use a net. And then there's the very large array, which goes deeper into space. That's not far from you guys out there. But SETI has relied upon very narrow band transmissions. And so what we've been doing up till now is SETT, the search for extraterrestrial technology. They only look at the narrowband carrier wave. They do not look at the broadband signal. And we would miss a broadband signal by current SETI technology. So in order to broaden the signal, and if nature can make broad signals, so what criterion do you use? Well, you have to learn what is intelligence, how do we define it? And we've decided that one of the things you can do is, first of all, you have to study non-human intelligence and generalize intelligence filters. And the other thing is you have to be able to characterize, have a mathematical proxy. And our proxy for intelligence, there are various kinds of intelligence, but the kind of intelligence that SETI will detect is communication intelligence. And in order to detect that, you have to know how complex the signal is. So we, in a way, are substituting, like you can substitute Antarctica for Mars. To do exploration of Mars and Antarctica is good practice. And good practice for us is to apply information theory to develop intelligence filters so we can tell at least the complexity of the signal that we're getting. And one first order intelligence filter to measure complexity is the Zipf plot. And Zipf law basically says that for almost all human languages, if you plot the logarithm base 10 of the frequency of occurrence of the signal in rank order, in other words, the most frequent compared to down to the least frequent, you will get a -1 slope for complex communication systems. And we found this -1 slope for dolphins. And of course, it applies to all human languages. And we also found that for human babbling, you get a slope of something like -0.6, maybe 0.5 for baby babble. And what that means is that baby babble is closer to random than modern human languages. And 2 baby dolphins were born at Marine World, and Brenda McCowan and Sean Hanser and I did this work. And basically, the baby dolphins had a babbling distribution. They had the same slope as human baby babble of about -0.5, something like that. So as they grew up, at about, if I remember correctly, 18 to 20 months, the baby dolphins grew into their whistle language and had a -1 slope. So what we were measuring is the degree of complexity growing as the babies went from babbling, the baby dolphins went from babbling their whistles to, modern vocalization. And you say, well, this law is universal. Well, it shows up whenever there are rules in the communication system. And so we can ask ourselves, will it ever be confused with advanced astrophysics? And the answer is, this is a Zipf plot of a pulsar. And pulsars used to be called LGMs because they're so organized. They were nicknamed little green men when they were first discovered. But it turns out they are understandable in the physics of neutron stars rotating, remnants of supernova. And they don't obey Zipf's law. So we can easily distinguish between a communication system, a language, in other words, and even very complex astrophysics. So this showed the relationship of the baby dolphin and how they got redundant, but not as redundant as humans. and then finally wound up with a -1 slope. So you can actually, for example, use this law to see progress in the complexity of learning in different species. And in the case of little dolphins growing up, they also increase the conditional probabilities between signals, which are called higher order entropies in Shannon information theory. I'll talk about that in a second. This shows different species, and not all species obey Zipf's law, so that means it can remain a diagnostic. Here is a plot of various things that approach Zipf's law, but don't hit it. Basically, you can overshoot it like the Arecibo message did. That means that, we sent a message out into space from Arecibo toward the globular cluster M13 in 1974, and it was a pictogram. So it didn't have any intrinsic complexity to it. And, I can't help but think that some aliens are out there wondering how somebody that could build a radio telescope would have an entropic complexity of 2, whereas humans have an entropic complexity, word complexity of 9. So, but and here's another ones there. You have to watch out for like Benford's law. You probably know about Benford's law. Is just the way that numbers distribute themselves naturally, because like, for example, if you count to 20, you have 9 1s and 2 9s. So Benford's law is what the Internal Revenue Service uses to see if you fake your taxes. If it doesn't obey Benford's law, then you filled in the numbers, not them, not the natural occurring numbers, and so on. So you can see there's a lot of comparison of things, but dolphins and humpback whales do land in the -1 slope complexity area, and these other things generally do not. And there is conditional probabilities between signals. In other words, we call that syntax in human languages. And that is a second order information theoretic measure. The Shannon entropies, basically, Shannon invented the term, as far as I know, he invented the term bit. And basically, the number of signal types, the log base 2 of the number of signal types, is called a zero order entropy. And this is a measure of kind of how many choices you have. If you have 1 bit, you get off and on. Think of it as a light switch. 2 bits, off, on, off, off, and on. That's the first order. You get probabilities being introduced. That is the frequencies of occurrence of individual signals, and that's called the first order entropy. The second order entropy you might think of as the diagram structure in the communication system. So I say I'm thinking of a second letter of a word, and you may guess E because it's the most frequent letter. But if I say, well, the first letter is a T, well, now you consider the letter H might be the second letter. And that's because you know conditional probability between the H and the T preceding it. And third order is, the second order, the third order, and so on are the conditional probabilities of signals upon each other. So you're introducing dependency between signals. And of course, what we're talking about is the F sub I term in the Drake equation. Kepler, last 2 decades, has basically nailed F sub P. We know that about 1 in 1.7 stars has a planet. And we're skipping ahead. This is the part of the Drake equation that generally isn't supported by NASA. They're just beginning to fiddle with F sub L, which is, looking at transits of planets and shining light through it. And they're looking for biomarkers, in other words, especially the ozone 9.6 absorption feature. But they haven't gotten to looking at intelligence features yet. But you can kind of predict what NASA's going to work on next by just going down the Drake equation. It takes about 2 decades to go from each term. So just to show a diversity of application, I applied information theory to this experiment these people did back in Pennsylvania, and they put a gas chromatograph in a bunch of cotton plants, and the cotton plants apparently have two predators. They have a wasp that likes caterpillars. We'll just put it this way, call them caterpillars. And there's a worm that also likes to feed on the cotton plant. And the cotton plant puts out certain 9 chemicals in different ratios, depending on whether it's trying to call the birds to eat the worms or the wasps to eat to predate on the caterpillar. So I did a information theoretic analysis of this, and the cotton plant's putting out about 2.4 bits, which means it has about 5.3 choices. So the wasp was 73% successful. So I thought, okay, why do you need 2.4 bits when you have a 1-bit choice? Well, there must be at least 3 more predators to the cotton plant, because why would you need a vocabulary of 5 if you only have 2 predators? And I got a nice phone call from Pennsylvania from the botanist, and they said, yeah, there are some more predators. How did you know? And I said, the cotton plant told me. So they said, well, maybe we can apply information theory, to plants. And so I'd like to see more of that. But in the meantime, our main critter is humpback whales. And
Laurance, can you hear me? There's 2 minutes left.
Oh, gosh. Okay. Well, let me skip ahead. Humpback whales make bubble rings to catch critters in. And we discovered syntax in the humpback whales by actually, let me just finish with this then, by actually measuring the channel capacity using information theory. And then using the channel capacity, we calculated that the humpback whales were not drawing out their signals enough to overcome the noise that they were encountering. And we thought about this for a while, and we finally realized, we had a Xerox machine that was low on toner, but we filled in the missing words. And we figured out the humpbacks are filling in the missing signals, so they don't have to follow the channel capacity exactly, because they have internal conditional probabilities that allow error recovery, namely syntax, what we call syntax in humans. So in other words, you can use information theory to discover all sorts of things that direct translation will not allow you to discover. So let me just end with that and show you some intriguing pictures, polar coordinates to analyze bees, and so on. Eventually, we'd like to wind up with an encephalization quotient based on information, something like this. And if we get an extraterrestrial signal, we can calculate the complexity without translating any of the terms. And if it turns out that we have 9th order entropy and they have 20th order entropy, we'll know where we stand. So in conclusion, are we alone? We have to quit looking up at the sky and saying, are we alone, when all these critters are on Earth? And I just want to add with one more, I'm going to turn this up, but Brenda talked about a communicative incident with humpback whale twain using a humpback whale signal. And let me just play, I'm going to write this up, but let me just play this intriguing possibility. Would you think humpback whales might try to communicate with humans in human? We'll see what you think.
I'm just going to play it quickly.
A humpback whale trying to communicate with us in human?
You're listening to humpback whale that sounded
Humpback whales making vaguely, slightly humanish sound.
That was a humpback whale.
humpback.
So was the whale trying to?
Twain apparently is smarter than we are because, you know, if somebody does that to you, you try and respond, and Twain responded at least, but as far as I know, humans did not respond to that.
So questions for Laurance?
I have questions. Laurance, what context did you get that? Was that truly a humpback whale sound that sounded human? What was the context of getting that signal?
Well, I got it from Fred.
Fred?
Yeah, it was part of those bubble netting teams, and a lot of times they, in between events, they're sort of reassembling and moving around and trying to figure out their next game plan. And so it was kind of one of those discussionary intermediate periods where, because bubble net feeding requires so many elements, the net and cooperation and sonification with these sounds of blasting the schools. If there ever was a system where there might be command and control information being exchanged, it could be this one. So I suspect it was one of those situations.
Laurance, just to know, Ted and I share a frustration that the three-body problem was wrong. Quantum teleportation is still causal and needs a classical channel. So even if they're using quantum teleportation for the qubits, you still need the classical channel.
Yeah, you still do.
Yeah.
And it saves relativity, right?
Yeah. Say it again.
It saves general relativity and special relativity. It's you have to have a classic channel to actually.
That's exactly right. It doesn't violate causality.
Yeah. The way I usually put it to students is that you can teleport the information, but you have to send the unlocking mechanism at the speed of light.
That's exactly right.
Yeah.
Okay. Thank you for that.
Thank you.